Hey guys, let's discuss new meta interview loop round, which is round 3 and called coding round 2. So here they have given you problem which is called word ladder. Okay, so word ladder means see here you would be given, let's see, one begin word, okay, one end word, and then one dictionary. Let's say in dictionary you have something like this. Your begin word is hit, okay, and your end word is cog, let's say, and your dictionary is hit, hot, okay, then dot, dog, and then cog. So now here you need to you need to convert this word to this word. Okay, so for example, H will convert to C, I will convert to O, T will convert to G. Okay, but in minimum transformation, and those words should be there in the dictionary. So for example, if directly what I can do, I can convert this H to C, right? That is the one thing. So it means that I want CIT in my dictionary. I don't have CIT in my dictionary, so I cannot go with that. Let's say I have CIT in my dictionary, okay, then I will convert I to O. So then I want COT in my dictionary. I don't have that, so I need to use those words which are there in my dictionary, and then I need a minimum words like that. So for example, this is very simple. Okay, you have to convert from HIT to COG. Okay, so first what you will do, you will take the first character and you apply all the alphabets here. Okay, you have 26 alphabet, so check whether you have AIT in the dictionary, BIT, CIT, DIT. Okay, check those things if you have that in the dictionary. After that you apply this, then you keep H as it is. Okay, then now apply that for the second word I. So I will become A, B, C, you apply for that. Okay, so HAT, HIT, something like this. And then for this third one, so this thing you will so at a time you will change one letter, right? So for example, you have HIT, so here you will convert this I to O, right? So it will become HOT. Now after this you will convert this, and HOT you have here in the dictionary, right? Then this H you will convert to DOT. Okay, now you have this DOT also in the dictionary. After that this T you will convert to G. Okay, so DOG, you have this DOG also in the dictionary. Now you will convert this DOG to COG. Okay, and you have this COG also in the dictionary, and hit though was already there. You don't need to cover all the words from the dictionary, but yeah, you have to convert from hit to cog. Okay, and then minimum words you will be using which are there in the dictionary. That is what you need to do. That's it. So see here, let me remove these things. Okay, and now let's discuss from starting. Okay, what is expected, what you will answer. So here we will be talking about two rules, which is E5 and E6. Okay, E4 can use the E5 answer only, not that rocket science. Okay, now so here expectation differ by levels. Okay, so E5 means senior software engineer, E6 is staff engineer. Okay, so E5 implement he will say that he will implement an efficient BFS solution to find the shortest transformation sequence. Why BFS? Because you are level wise, you are traversing like HIT. So first for H you will find all the levels A to Z. For I you will find all the levels from A to Z. Then for T you are finding A to Z. Okay, now once you change it for that level, you will again find all the levels. So level wise we are traversing here. That's why BFS we are using here. And E6 is staff engineer, so he will discuss bidirectional BFS. So means bidirectional BFS means, see, you start from here also and you start from here also. Okay, you will meet here. So for example, here you would be required 1, 2, 3, 4 words conversion. Okay, so in this case you will need 2 words from here, 2 words from here, 4 only. Means yeah, for the means half only, right? 1 here, so 2. Okay, so that is the bidirectional BFS. Okay, then large dictionary optimization. If this dictionary is very large, then what you will do? Okay, parallel search also you can do. Means from, let's say you have a 100 million words in the dictionary, so for 1 to 10 you give for the worker 1. Okay, parallelly they will do. from 10 to 20, worker 2 will work on that, okay, something like that, and later they will merge the answer. Then memory optimization and distributed implementation. Problem statement: given begin word, end word, and dictionary, transform one word into another by changing the one character at a time. Every intermediate word must exist in the dictionary and find the shortest transformation length. So we have seen that, right? So now if I senior software engineer, what he will say, I will model each word as a graph node. We have seen that, right? Two words are connected if they differ by one character. Since every transformation has equal cost, BFS guarantees the shortest path. So here you will build the dictionary, okay, then BFS queue, it will go to BFS queue. From there it will generate the neighbor, and then it will visit the new node and then reach the end of the word. So Java solution, if you wanted to see, so here what is happening, see, this is ladder length is your main class, class function, and you would be given begin word, end word, and then list of word list. Okay, so now you will create one set, and inside that set you will put all the word list so that duplicate will get removed. Okay, so this one dictionary you have given, right? So you will put that in a set. Now you will see you need to convert from begin word to end word. So first you need to check that end word exists in the dictionary or not. That is the very first condition for the validation, right? So you will check if that end word is not there in the dictionary, then just return 0. Otherwise you will create one queue, okay, and just add the begin word in the queue, right? And then create one set also visited. So here we will maintain all the words whether it is visited or not, okay, then you don't need to visit it again, and add the begin word in the visited also. Now let's talk about level 1, because here you're going the level wise, right? So you will until queue is not empty, you will apply this thing, okay? So let's say you have HIT, you have one queue, and you have one visited array. So initially begin word was HIT only, so you will add that in the queue and you will add that in the visited also. Now you take that you just check the size of the queue. Right now it is 1, okay, and for that then you will poll the first element from the queue. So let's say that is the word, so this one you have taken from the queue, okay, and then first check whether this word is equal to end word or not, okay, but currently it is not equal, so otherwise you return level. So now what you will do for HIT, for each character of this word, okay, first you convert that into the character array. Now for till that for each character, okay, just get the original array. So for original character, so for example this H, so now you will check it for the AIT, BIT, CIT, okay, ZIT, ZIT, and first you preserve this H into the original, okay, so original will have the H, then you check from A to Z, okay, all the character, if it is there in the dictionary, okay, and it is not visited, then just add that into the visited and add that into the queue also, because now we will proceed from that character, okay, and then you again change the original character, because for HIT, okay, so for H it is done, for AIT, BIT, so you will put that H as it is. Now you will do that for I, okay, HAT, HBT, HCT. Now once it is done, you will again change it to I, and then you will do for this T, HIA, HIB, HIC, something like that. Otherwise you will do the label plus plus, okay, and then we'll take the another character from the queue, and at the end you will just return 0, otherwise you will return the level. So the complexity will be n into L into 26, okay, time complexity 26 character for A to Z. L is the number of word length and n is the number of words, okay. Same space complexity will be order n number of words, right? So E6 will say for production systems with millions of words, I would use bidirectional BFS pre-computing wildcard indexing and memory efficient data structure and distributed search to minimize the latency. What is pre-computed wildcard indexing? Let's say you have a millions of words in the dictionary, okay. Now if you go and check whether this, let's say AIT, you will check this AIT with that millions of word, okay, later you will check this BIT with that millions of word, so that is not possible, okay, that the complexity will be very high. So what you will do, you will use the wildcard indexing. What is wildcard indexing? See, for HIT you will create 3 patterns. First one is star IT, second is H star IT, and third one is H, I and star. Okay, first position, second and third position. Now in that dictionary you will pre-compute, okay, you will pre-compute all the words whose pattern is this, all the words whose pattern is this, okay, and then directly using the VLOOKUP, okay, using the lookup you will check whether this one exists in that pattern, this one exists in that, and this one in that. So in this way your space complexity more, okay, but the time complexity will be less. So here is the trade-off, you have to choose otherwise the space complexity or the time complexity. Okay, now the next question is why BFS? Why we have used here BFS and not DFS? I've already explained. Level wise we are going here, okay, instead of width wise, length wise. So see, if I will say that each transformation has the same cost, BFS always find the shortest path in the unweighted graph. DFS will see, E6 will say that DFS may find a valid path but not the shortest one. BFS guarantees the optimal, okay. Follow-up question 2 is bidirectional BFS. From here also you will start, from here also you will start, at the end, at the mid, okay, they will meet and there you will compute it, something like this. If run BFS simultaneously from begin word and end word, okay, then stop when the search meets. So E6 will show you something like this. You have to change hit to cog, okay. So first hit will go and change it to hot, then dot, okay, and similarly cog will change to dog and then dot, okay, and then after that dot will change to, and here a dot is common, right? So here you will know that okay, this is the answer. So instead of 1 to 2, 2 to 3 means 4, 5, 6 comparison, you have done only 3 comparison. So that is how you can do the bidirectional BFS search. Now this significantly reduces the search space and is a preferred approach for large dictionaries. Now follow-up question 3 is large dictionary optimization, okay. So store words in the hash set for order 1 lookup, E5 will say, and E6 will say pre-compute wildcard pattern, what I just explained, like hot. So you will create 3 patterns here, okay. This allows fast neighbor lookup without comparing every word. Follow-up question 4 is saying memory constraint, okay. So E5 will say remove visited word from the dictionary to reduce memory usage. If it is visited, remove it from the dictionary itself, no? Why to keep that? So then you will save the space there. E6 will say optimize with compressed dictionary, okay. Use the compressed dictionary, try based storage, lazy neighboring neighbor generation, and then memory mapped files for very large data sets. So follow-up question 5 is generate neighbors efficiently. E5 will say replace each character with letter A to Z, and E6 will say use wildcard indexing, okay, the same thing what I said, and then do the dictionary lookup, okay, and then find the answer. Now follow-up question 6 is weighted transformation. So see, right now our weight was 1 only for each, right? From HIT to HAT weight would be 1 only, but what if the weight is different, okay, then you cannot go with the BFS. If I will say if transformation have different cost, BFS no longer works. E6 will say then in that case use Kahn algorithm for non-negative weights. If you have non-negative weights, then we will go with the Kahn and not the BFS. Okay. Follow-up question 7 is return all shortest path. Now you have to return all the shortest path instead of one shortest path, all the shortest path, okay. So how you will do that? Very simple. If I will say store parent node during BFS and backtrack after reaching the target, what we do in the normal tree questions, right? I've created data structure playlist, okay, pattern wise. You can go and check. It is like 2 to 3 minutes question which are very important. You can see directly in the interview. Those questions I have explained in 2-3 minutes only. So you can go and do the revision there. Quick revision, okay. Now E6 will say use BFS to compute minimum distance and DFS or backtracking to reconstruct the every shortest path. Okay, only 2 follow-up questions are remaining. Follow-up question 9 is dynamic dictionary updates. So if I will say update the dictionary before starting a new search, and E6 will say support incremental updates. Incremental updates means new word came, okay, so update the index and refresh the wildcard map, and then do for the future search, okay. So avoid rebuilding the entire index. Follow-up question 10 is complexity analysis. So if I will say without optimization, the complexity was order n into L into 26 and space complexity was order n. With wildcard indexing, the bidirectional BFS, you are using bidirectional plus wildcard indexing also, okay? So neighbor lookup become much faster, search space is significantly reduced, and practical latency improves substantially, especially for the large dictionaries. So that's it.